You know that feeling when you wish life had an undo button for wrong turns? Well, in the world of algorithms, it kinda does. Today, we're going to demystify a super powerful technique called backtracking. It's this amazing strategy for tackling really complex problems, and you'll see it all boils down to one simple idea. All right, so let's jump right in with a classic puzzle to get our brains going. Imagine this. You're standing right at the entrance of this maze. You've got no map, no bird's eye view. All you can see is the path directly in front of you. So, what do? How do you possibly find your way out? So you pick a path, right? You walk down it for a bit, maybe take a few turns, and then boom, you hit a wall. It's a dead end. The path you chose? Yeah, it was the wrong one. So what's your move? What do you do now? Well, you do the only logical thing, don't you? You go back, you retrace your steps to the last intersection, the last place you had a choice, and you try a different path. And that right there, that super simple, intuitive action, that is literally the entire idea behind backtracking. That's it. So this instinct to just go back when you mess up, it's not just a neat trick for solving mazes. Turns out it's a really fundamental way to solve all sorts of complex computational problems. So let's formalize this a bit. Let's give this strategy a proper name and some structure. And I absolutely love this analogy. The key part here is blindfolded, right? It means you have no idea what the best path is from the get-go. You can't see the whole picture. You just have to explore, you have to make a choice, and this is crucial. Be totally ready to admit that choice was wrong and undo it. Okay, so we can actually break this whole thing down into a really simple, repeatable loop. It's basically 4 steps. 1, you explore a path. Just pick one and go. 2, you hit a dead end or realize this path isn't working. 3, you backtrack. You go back to your last decision point. And 4, you try another path. And you just keep doing that over and over and over until you find a solution. Okay, so that's the intuition. But how does this simple, almost childish idea of solving a maze, how does that transform into a powerful algorithm that computers can use to solve insanely complex puzzles? Well, let's take a look under the hood. So, here's the more formal definition. Backtracking is a technique where you build up your solution piece by piece, incrementally. But here's the really clever part. At every single step, the algorithm asks itself a question. Is it even possible for this path to lead to a solution? And if the answer is no, it doesn't waste another millisecond on it. It just abandons that path and goes back. The way this whole process works is that it creates what's called a state space tree of all the decisions. Think of it like this. Your starting point is the root of the tree. Every choice you make creates a new branch, and backtracking explores this tree by going deep down one branch, as far as it can possibly go, that's called a depth-first search, before it hits a dead end, backs up, and tries the next branch over. All right, to make this really concrete, let's look at a classic example, the 4 queens problem. The goal is pretty simple to state, but tricky to solve. You have to place 4 chess queens on a 4x4 board in a way that none of them can attack each other. And if you know chess, that means no 2 queens can be on the same row, the same column, or the same diagonal. So how would an algorithm tackle this? Well, it starts by just plunking a queen down in the first square of the first row. Easy enough. Then it moves to the second row and looks for the first available square that's safe, where a queen wouldn't be attacked. It places the next queen there. And it just keeps going like this, building a potential solution 1 row at a time. But what happens when it gets to, say, the 3rd or 4th row, and it realizes there are no safe squares left? Anywhere it puts the queen, it's going to be attacked. It's stuck. That's our dead end. And now the algorithm does its magic. It says, okay, this whole path was a mistake. It prunes that entire branch of the decision tree. It backtracks. It literally goes back to the previous row, picks up that queen, and moves it to the next available safe spot. And it just keeps doing this. It explores, gets stuck, backtracks, tries something new, explores, gets stuck, backtracks over and over again. Until, finally, it successfully places all 4 queens on the board and nobody can attack anybody else. And that's it. We're done. That's a valid solution. It has successfully navigated that big, complex decision tree to find a winning path. Now here's what's so cool about this. This single, simple idea, just go back when you hit a wall, can be used to solve a massive variety of problems. Problems that, on the surface, look like they have absolutely nothing in common. I mean, just look at this for a second. On one hand, you have a messy, tangled, chaotic maze. On the other, a perfectly structured, logical chessboard. They feel like they come from totally different universes, right?
But the core logic, the fundamental algorithm a computer uses to solve both of them, is exactly the same. Explore a path, hit a dead end, go back, and try again. That's it.
And the list just goes on and on. This same idea is the key to solving so many things. We're talking Sudoku puzzles, generating every possible password from a set of characters, word searches, the classic rat in a maze problem, even things like graph coloring. These are all problems that pop up constantly in coding interviews, and backtracking is the tool you need.
So, okay, this is all great, but it brings up a really critical question for any developer, right? You've got this whole toolbox of different algorithms. So when, exactly, is backtracking the right tool for the job?
And this is where a lot of people get tripped up, especially when they're trying to decide between backtracking and another heavy hitter, dynamic programming. I mean, they both seem to solve big problems by breaking them down into smaller pieces. So how in the world do you choose? Okay, so this table really lays out the key differences. I like to think of it like this. Backtracking is like a really thorough but smart explorer. It's determined to check every single possible path to find all the hidden treasure chests, but it's smart enough to stop going down a path the second it sees a dead-end sign. Dynamic programming, on the other hand, is more like an efficient factory manager. It breaks a huge project down into tiny, repeating tasks. It solves each tiny task just one time, stores the result, and never ever does the same work twice. That incredible efficiency is what lets it find the one single, absolute best way to do something. So, if you need a simple rule of thumb, here it is. If the problem asks you to find all the possible solutions, like list every single way to solve this Sudoku puzzle, your brain should immediately scream backtracking. But if the problem asks you to find the one best or optimal solution, like what's the absolute minimum number of coins I need to make this change, that's a massive clue that you should be looking at dynamic programming. So when you think about it, backtracking teaches us this really powerful lesson that goes way beyond just code. It's a reminder that sometimes the only way to truly move forward is to have the courage to take a step back, admit a decision was wrong, and try a totally different path. It's really the art of the second chance built right into an algorithm. So the question I want to leave you with is, what impossible problem in your life could you solve by simply being willing to take a step back,